presenter, Delphine Genovrier, who will be with us talking about flow simulation. Delphine has been in the simulation arena for many years and originally started with SRAC, Structural Research and Analytic Corporation, in 2000 as an applications engineer. SRAC was acquired by Dassault Systems in 2001 and is the FEA solution we now use in SolidWorks simulation. Delphine has had many roles focusing on simulation while at SolidWorks, from business development manager to product manager, where she works today for flow simulation and 3D Via Composer. Welcome, Delphine, and thank you. It's now all yours.
Thank you, Amy, and hello everyone, and thank you for joining us for this webcast entitled SolidWorks Flow Simulation in 22 minutes. Today's presentation is all about a discovery of CFD, and more particularly SolidWorks Flow Simulation, and how CFD can help you facing your business pressures. We'll review together a concept called Concurrent Engineering and see together how these apply well to CFD. Then we'll discover together what is SolidWorks Flow Simulation, how it can help you during your product development cycle to get meaningful insight for your technical decision. Okay, so let's get started. In today's environment, companies must address many different factors in order to be successful. A key business driver for companies is the innovation. Finding the best and the newest product to stay leader in your market or to win new market share is what makes managers awake in the night. But creating better or more effective product, processes or technologies that are accepted by market is not that straightforward. Indeed, companies are striving to design innovative products while reducing the cost of product development and time to market. Therefore, companies every day need to find the right product development cycle to balance cost and time to market to come with the best product for their customers and prospects. The pace of product innovation has increased dramatically in the vast majority of the industries. The companies are then changing and optimizing their product development cycle to answer these business pressures. Some of you might know the consulting company called Aberdeen Group. Aberdeen is a provider of fact-based research and independent third-party validation for best-in-class practices. Each year, they conduct hundreds of primary research studies through surveys and interviews. A 2011 market survey has been conducted by Aberdeen Group on more than 700 companies that develop products that are impacted by fluid flow. The goal was to provide them guidance to help companies to make better design that will lead to more profitable products. One of the key data is that product development needs better insight into product behavior to address time, quality, and cost pressures. They found out that business pressures such as shortened product development schedule, competition, and customer demands for lower cost product but at the same quality drive companies to better understand product behavior during the development process. But the key challenge that companies face when they want to improve their knowledge of product behavior are the fact that products are becoming increasingly complex. Many products have evolved into complex systems of mechanical components, electronics, and software, involving multiple engineering disciplines. In addition, the increasing number of components, often combined with miniaturization, requires an even greater understanding of how they will interact while making sure they do not overheat, for example. Another challenge is that product performance is impacted by multiple physical forces. These forces, coupled with the complexity of the product, makes predicting how the product will function in the real world pretty difficult. These challenges create a need for improved way for assessing product behavior. Standard testing methods or the experience are not enough anymore. Addressing these challenges will allow companies to improve the overall product integrity and then answer business pressures. When designing and manufacturing products that are impacted by fluid flow, it is then crucial for the product development team to be able to test their product while designing it. This is what we call concurrent engineering. But before we go further, let me ask you one question. Today, in your engineering department, how do you test your design? So you will see a poll question on your screen. So please let us know if, to test the performance of your product, are you doing prototyping? Are you outsourcing virtual simulation to external company? Are you using already yourself, some FEA, CFD, or kinematic simulation? Are you not doing any test before manufacturing your product? So let me wait a little bit to see the results.
So Delphine, while we wait for a couple more people to chime in, we have about 53% doing physical prototypes, 24% doing FEA analysis, 10% doing CFD analysis, 9% are not doing any testing, and 4% say other. Last chance to give us your answer.
Yeah, this is what we see. Yeah.
Okay. Go ahead.
Okay, thank you. So this ratio is usually what we see on the field. So lots of companies are doing real prototyping to test the performance of their product, or unfortunately are not doing any test and kind of hoping that it will work as planned in the real world, or unfortunately very often are over-dimensioning their products. So we will see together how virtual simulation, and today more particularly CFD, embedded into your design process and not done at the end, such as prototyping or outsourced simulation, will help you to get better insight for your product performance. So traditionally, product development is a sequential process. From the concept of the product until its manufacturing, engineers go through steps of design, testing, technical product publication, manufacturing, one after one. The testing phase is done either by physical prototyping, as we've seen today, outsources calculation, or sometimes only by some type of manual testing or experience. CFD, or fluid flow analysis, has been traditionally conducted at the end of product development for verification purposes only. To optimize and check design performance, companies are now integrating fluid flow testing into the design process. This means that they can make design changes early in the design cycle when it is still possible to do so and it is not too costly. They are then getting the benefit of early flow analysis, such as an increased quality of their design by validating them in progress, conducting what-if studies, and not only improve design but also get them to market faster. The objective is then to conduct fluid flow simulation as a concurrent task during the design process in the concept or in the detailing design phase, and not only at the end of the cycle, with real prototyping, when usually it is too late or too costly to make major changes in a design. So running CFD simulation during these phases will help you compare design scenario and find the best one, testing new devices and seeing if they improve product performance while decreasing time to market. So we mentioned already that acronym CFD. So what is CFD? To simply state, fluid flow analysis of CFD, computational fluid dynamic, is a virtual simulation of the flow of real-life fluids such as water or air and heat transfer problems. Almost every design is impacted by fluid flow to some extent, from wind loading to airflow inside components. Engineers designing products that relate to flow of gas, liquid, heat transfer and forces on solids can greatly benefit from this CFD simulation. Indeed, understanding and accounting for flow can be an important part of the design. The challenge is to understand something you cannot see or easily measure, for flow field and fluid pressure in valve or piping, for example, heating or cooling phenomena around electronics, or turbulences phenomena, and many more. So if you are designing and manufacturing a product impacted by fluid flow and heat transfer, CFD will
choose internal analysis, 29%. I'm sorry, for liquid flow, 29% for gas flow, 11% external for gas flow, and 5% external analysis for liquid flow, and 8% other.
Okay, so the vast majority of you are interested in knowing more, how the fluid is flowing inside my product. And this is usually what what our customers are doing, running CFD simulation during design cycle. So, for example, if you are designing an electronic enclosure, you want to know how the air will flow around your components inside the enclosure to understand the cooling phenomena. Or if you are designing, for example, a medical device, you would like to know how the blood will flow inside your device to reduce the dead zone phenomena, for example. So it makes a lot of sense according to what we see on our customer base. So we spoke about what is CFD. So what is SolidWorks Flow Simulation? So SolidWorks Flow Simulation software is a powerful CFD tool that enables designers to quickly and easily simulate fluid flow, heat transfer, and fluid forces that are critical to the success of the design. SolidWorks Flow Simulation is fully integrated within SolidWorks 3D CAD software. So you can use all the benefit of a fluid flow simulation to design your products with better insight. Design variation can be compared to make better decisions, resulting in product with superior performance. You can, for example, simulate the water flow inside a valve to dimension it, getting the pressure drop, velocity result. You can test the airflow inside an electronic enclosure to optimize the cooling process, or check the airflow around vehicle among a broad range of applications. Concurrent Engineering helps detect design issues early in the design cycle and helps compare design scenario before going further in a design process. With SolidWorks Flow Simulation and a wide range of technical capability that you can see now on this slide, you can gain an understanding of the impact of flow on the design before it is built. So what type of engineering challenges does SolidWorks Flow Simulation address? Here is a slide of typical application that we can see on our customer base. Pressure drop is a term used to describe the decrease in pressure from one point in a pipe or tube to another point downstream. This parameter is a standard result that CFD engineers are looking for. For example, the objective of a duct design is to size the ducts so as to minimize the pressure drop through the duct while keeping the size and then the cost of the ductwork to a minimum. SolidWorks Flow Simulation helps designers to investigate and optimize pressure distribution in a wide variety of products such as valves, nozzle, control devices. Flow fields. When you are designing a product in which or around which fluid is flowing, it is important to understand the fluid flow behavior, to get the fluid velocity, the fluid trajectories, and to have an idea about the turbulence risk. With SolidWorks Flow Simulation, you can inspect and optimize complex flows in and around product with internal and external analysis. It transfers throughout an environment all the time. Wherever you are aware of things that are warm or cool, or that are getting warmer or cooler. This is a very common challenge in electronic devices, for example. Indeed, they have less and less space to provide airflow as they are smaller and smaller, so it is an ongoing thing that needs to be prevented in order to keep the equipment in good health. With SolidWorks Flow Simulation, you can simulate fluid flow as well as coupling it with heat transfer, such as convection, conduction, and radiation. Designer can apply heat sources, thermal properties on components, define fan position, for example, and then get as a result the temperature distribution, both for the fluid and the product itself. So these are typical applications, but obviously SolidWorks Flow Simulation is appropriate for many more applications. Another question for you. We asked you, what type of tests you're doing on your design. So you told us, physical prototyping, no test, or some people are doing some outsourced simulation. So I would like to ask you, With your current approach, with your current method, do you find it easy to understand the performance of your product based, only on experience and prototyping? If you think about your product, not only when you face, a big issue when you manufacture your product or when your customer call you for a problem, but more when you try to optimize your product or to make a better product. Do you find your current processes, efficient enough for your company?
Delphine, we have about 80% saying yes and about 20% saying no.
Okay. So I guess for the 80%, as a majority of you answer that you are doing prototyping, you think that, it is enough for you because with a real prototype, obviously you see how the product behaves in real life, and you understand and you can validate if your product will work as planned. But what you need to understand is that lots of company, you cannot do a prototype for all of your products, and you will do a prototype only at the end of the product development cycle. So if you think about optimizing your product and testing all your products you are designing, not only the most critical one or the most expensive one, but trying to test the performance of all of your design, this is what SolidWorks Flow Simulation, of more in general virtual simulation, is all about. The capability to test all of your products earlier than what we do with real prototyping. So now let's discover today the software itself. We cover, what it can do and the philosophy of doing virtual simulation inside design process. So now let's see how this product works. So today the example I will demonstrate is a consumer convection oven. This model involves both fluid flow, so airflow, and heat transfer. A wall oven uses electric heating elements to generate heat over a range of temperatures. So the heat is convected into the surrounded air, which then moves to heat the cooking volume. A fan oven employs a fan to speed up the warm-up time and achieve a more uniform temperature distribution. So today, for this example, we will look at how to set up the CFD analysis in SolidWorks Flow Simulation, and more importantly, how to access the result for design insight for lots of design scenarios. Is what I just mentioned. Use, virtual simulation not only for one product, but for all of your product design scenarios so you have in mind when designing your product. So you can see here we have two configurations of this oven, and we'll test this model in SolidWorks Flow Simulation for these two design scenarios. So let me show the demo video, and we can start having a look on the product together. So just wait, because sometimes it takes a little bit of time to share a video. I hope you can see my screen. It seems that you still see PowerPoint, you do not see the video. And let me check why it's not working. Sorry for that. Okay, just take some time to refresh the screen. Okay, so let's get started and discover the product together. So as already mentioned, this model is a consumer convection oven. The goal of the CFD simulation is to validate uniform temperature distribution for two design scenarios, one with one tray and the second with two trays. SolidWorks Flow Simulation is fully embedded inside SolidWorks, so users can test and validate design scenarios easily. Here in SolidWorks, two configurations have been defined, as you can see. So first, let's take a look on the configuration with one tray. With an intuitive wizard, the CFD analysis is set up. The CFD analysis name is defined, so for example here we'll call it Study 1. Then we'll define the default unit system that is predefined in SolidWorks Flow library called the engineering database, and you can fully customize it with your own unit system, for example. Then we'll define the default assumption. As we are only interested in the fluid flow inside the oven, we consider the fluid region to be internal. Heat conduction in solids is enabled to consider heat transfer by conduction. In this example, we do not consider radiation, but this could be turned on for a more complete heat simulation in flow simulation. This will be a default steady state analysis, and gravitational effects are considered for natural buoyancy purposes. The fluid by default for that example will be the air defined in the default SolidWorks Flow Simulation library. Then, the default material for the model is cast alloy steel and will be applied to all parts unless otherwise specified. And this material library has been defined by the user. So you have in engineering database a predefined solid data that you can customize for your own data. Then a heat transfer coefficient is applied to all external walls to take into account heat flux outside of the domain. And an external temperature of 25 degrees Celsius is applied for the external fluid domain. Initial temperature and pressure are by default value at sea level. So here we've defined our general assumption inside SolidWorks Flow Simulation. Now inside SolidWorks, SolidWorks Flow Simulation appears in the analysis tree, and we can see now that we will define the different assumptions such as the boundary condition, the solid material, the heat sources. So we'll do that together. So next, the various material properties are defined. We already defined the default material as cast alloy steel. So a 1060 steel alloy is applied to the internal wire type support frame. So very simply, we just need to select those two parts and define the material for these two parts. Plate glass is applied to the two panels of glass of the window. So in the same philosophy, we just need to select those two glass and define with the engineering database the material property. In SolidWorks, for example, here a customized scale property has been defined when we design this part. So this property can be then used inside SolidWorks Flow Simulation. So if you already define your property in SolidWorks, we can reuse them automatically in Flow Simulation. Finally, polymer is applied to the other components, including the cooking control and readout display. For the next step, heat sources are applied within the oven. For the simplified representation of this oven, the heating elements are not modeled explicitly. So instead, a fixed temperature of 220 degrees Celsius is applied on the heating element location. Other options to apply heat source can be, for example, power dissipation in watt or power dissipation per unit volume. As we are modeling this oven as a fan-assisted oven, we specify the correct fan. The fan is located at the rear of the cooking volume, just here. And an internal fan will then be applied to simulate the effect of the fan without modeling it in full detail. So we'll select here an internal fan in Flow Simulation, and the fan curve can be picked out of the pre-installed SolidWorks Flow Simulation library, as you can see now, or imported from a user database. So now that we have set up the main feature of the CFD simulation, so we define the boundary condition, so the internal fan, we define the heat sources, and the solid material of each part, we can solve the analysis. So now let's move on the result functionality of SolidWorks Flow Simulation. SolidWorks Flow Simulation provides a wide array of tools to allow us to understand the performance of our design. Section, surface plot, flow trajectory, and numerical result are used then to validate that our goals are met. We'll start with the cut plot. The cut plots are 2D representation of the result, which can be created on any plan of the model, so either SolidWorks plan or customized plan. They can be moved by dragging them and can display a variety of parameters such as velocity, pressure, or temperature. So here what we see is a cut plot of temperature inside the oven, and you can drag that cut plot inside the oven very easily. Multiple cut plots can be created at once also. So we'll create here another cut plot, and the current view shows the temperature distribution through the vertical center line of the geometry. So we can see here then very easily the temperature distribution inside the cooking volume with the heating system around. Then the probe tool is used to report results such as temperature value at desired location. So very easily you will get the local value when you want. And obviously other parameters such as here velocity can be shown by example in any cut plot you have defined. Surface plot uses existing CAD geometry to overlay CFD result on desired location. As we can see here, the part is hotter toward the rear of the oven where the fan is located. The next surface plot that you can see now show the door and the door of the oven, colored by temperature as well as the whole oven. It is clear that the hot center section is well insulated from the outer surfaces of the oven. This is primarily due to the space between the inner and the outer wall of the oven. Obviously, material choice also plays a role in thermal insulation. So very quickly, you can see the different temperature distribution on any kind of result distribution in flow simulation. Flow trajectory shows the path fluid takes through the fluid flow region. So this type of plot shows how the fluid is moving, which is very difficult to get in a physical prototyping, obviously. So you better understand if you have any risk of recirculation of turbulences. So now let's take a look on the second configuration with two trays. Notice that the setup is similar to the previous configuration. And so the first simulation will be very simply copy and paste to the second design configuration. This saves you time to use CFD as a design tool and validate as many design scenarios as wanted. The result plot has been saved as well. And so very easily, you can create, let's say, 10, 20 SolidWorks configuration, copy and paste your analysis, and you will be able to compare the performance of your different design scenario. So here you can visualize the temperature distribution for this second design configuration. It is very clear that the distribution, is not uniform. The cake position on the below tray will get less heat than the one position at the top. With the probe, we can see here the local temperature values. The surface plot shows these temperature differences on the plate as well. So on the one which is on the top level and the other one. So SolidWorks Flow Simulation helps you to compare different configurations easily without even leaving the SolidWorks environment. That means that you can test and optimize your product with CFD analysis during the design process and not only at the end, which usually it might be too late to make any design change in your design office. So let me reuse PowerPoint. Just wait so your screen is refreshed. Okay, so to summarize, CFD simulation that we've seen today is a powerful design tool which enabling product development team to make better design decisions. This has a direct impact on the success of your overall design. Switching to concurrent engineering, which means doing CFD simulation during the design process and not at the end, helps product designer to test as early as possible the product performance and identify possible design issues when it is still possible to make design changes. This helps to accelerate your product development cycle. So I hope that this first introduction of the benefit of SolidWorks Flow Simulation has been interesting for you. Obviously, this is the first webcast that we are doing this year on Flow Simulation, and we'll do many more. But we would like to ask you, before ending this presentation, what is your level of interest in SolidWorks Flow Simulation? So you have another poll question screen on your screen. Okay, so Cliff, I guess we'll go to the second one. And according to, obviously to your answer to the previous one, we would like to help you getting more information. So if you want, further information from us, please let us know. So we'll contact you and provide you maybe more in-depth information or information according to your own product or your own industry. So do not hesitate to request more information.